All right, the first modern astronomer we're going to talk about is a guy named Nicholas Copernicus. And Copernicus lived from 1473 to 1543. Okay. Copernicus, sometimes referred to as the father of the Renaissance or the change. Well, it's hard to say one person is because it was a whole idea of renewing, relearning, letting science and logic take over instead of religion. Okay? Up until then, through all the Dark Ages, the most powerful thing was the church, and the church told what people to believe and how to think. And it wasn't until this Renaissance, which was a rebirth or a learning what the Greeks did and then pushing it forward. And Copernicus just happened to be the first one, and he kind of spurred it on by this one idea. He was looking at, by this point, remember we're in the 1500s now, it's been about 1300 years since Ptolemy's model. Ptolemy's model had come back, had been translated back into Latin, and was kind of spread around Europe to these people that were studying. Copernicus actually was taught in science and medicine at the time. He went to school. Actually trained in law and medicine, sorry. But he had an idea. He said, you know what? That is Ptolemy's model is very, very complicated. Because you have these deferent circles, you have epicycles, they're all going at different speeds on different ones. And I didn't even show you all of them. The truth is the planets move up and down a little bit too. So you actually have one coming in and out. So it got really complicated model. And by this point, when you put all the numbers in, it didn't really match anymore where the planets were. And so Copernicus' whole view was to say, well, maybe there's a simpler way of doing it. And so he said the simpler way is, hey, let's put the sun at the center. So he came up with what we call the heliocentric model. Now, he probably wasn't the first one to think about this, but he was the first one to actually write a book on it and to explore it as a possibility. And there's some interesting things that occur when you put the sun at the center. It actually is supposed to make it much simpler. Well, it is. And this is the way the real world is, right? Sun's at the center, everything goes around it. One of the advantages to the heliocentric model is he could determine the distances to the planets. Which you can't do in the Ptolemaic model. We don't know how far away those circles are. It doesn't really matter if they're further away, the circle's bigger, but you can't tell. But you can tell in a heliocentric model. So imagine this is the sun, Earth going around. We know that the distance from the Earth to the sun is going to be 1 AU. If we have a planet like Venus, an inferior planet going around, when it's up here at greatest eastern elongation, so that this is a 90-degree angle, this is Venus, and this is 1 AU, all you have to do is measure this angle, then doing a little simple geometry or trigonometry, you can get the distance right here, the distance from Venus to the sun. And so you can figure out how far away Venus is from the sun in terms of the Earth-Sun distance. You can do the same thing for Mercury. It's a very easy thing. Now the trickier thing is to do it for the superior planets. So I'm going to show you how he did that. He did this. He said, okay, here's the sun, here's the Earth, and here is Mars at opposition, so that they all make a perfect line. And then the Earth is going around, Mars is going around, they're all going forward, okay? But Earth moves faster than Mars. And so Earth gets to a point over here, so Earth has moved from here to here. In that same time, Mars has moved down to here, so it hasn't gone quite as far in its orbit. Missed that a little bit, let's put Mars right here. So Mars moves from there, at the same time Earth moves here. So Earth goes through this angle, Mars goes through this angle. But remember, down here, this is eastern quadrature, because you do this when this is exactly a 90-degree angle, like that. Okay? Remember, it's eastern quadrature because if I rotate this up, that's where Mars would end up. Okay? And so, we have Mars in eastern quadrature. We know this angle. Now to figure out this angle, we have to do some tricks because we say, well, we know how fast the Earth moves. It takes 365 days to go around once. So we just know how many days from opposition to this. And we say, okay, each day it goes 1/365th of a circle. You just add up how many days and you figure out what that angle is. That's how you get this angle. They also knew how long it took Mars to go around, so they got this angle. They subtract those two, they get this angle, and then once you do that, you know this is 1 AU, and you can get the distance from Mars to the Sun. Don't worry, I'm not going to make you calculate those things. But that's how we did it. And so we had to know opposition and quadrature for each of the outer planets, and he could get that. But they had those details. They had the time when those things occurred. It allowed him to calculate that. Now the good thing about it is it was pretty accurate. For what he got was this. Just to show you his accuracy. He calculated that Mercury was at 0.38 AUs from the Sun. It's actually 0.387, so he's very close. Venus he calculated at 0.72, is actually 0.723. Mars he calculated 1.52. It is 1.52 away. He got it right on the money. Jupiter 5.22, it's actually 5.20. And Saturn he had as 9.18, it's actually 9.54. So he was really close to getting the actual distances to each of the planets using his system. All right, so he figured all this out. However, he had a problem. He used perfect circles. And the orbits of the planets are not perfect circles. And so when you use perfect circles on an ellipse, it doesn't match. And so because of that, he realized, oh, well, to make it work, I actually have to add an epicycle, just like Ptolemy had, to correct for the fact that it wasn't a perfect circle. And then he had to have one coming out of the page, too, because it didn't actually go in the same plane. It would go up and down. And the problem is, Copernicus' idea was to get a simpler view of the solar system, a simpler model. It ended up being just as complicated, if not more complicated, than Ptolemy's model was. However, it wasn't the model that mattered. What mattered was he changed the idea of having the Earth at the center. In science, we call this a paradigm shift. He shifted what everybody thinking one way for a long, long time, and then somebody said, no, think of it this way, and boom, everybody's like, whoa, brand new idea. Changes the way everybody looks at it. That's what Copernicus' book did, okay? We have those occasions. They don't happen very often. Einstein, when he started talking about relativity and time being a variable, it just blew away everybody in physics. They go, whoa, that was a massive paradigm shift. Okay? So this is his title of his book right here. It said it was technically called De Revolutionibus Orbium Coelestium. I'm not sure I'm pronouncing that quite right. But it's on the revolution of spherical orbs. Okay? Or essentially it was on the revolution of the planets. Now, just to give you a little more history here, Copernicus was Polish, up in Poland. So he was up in northern Europe. And at the time, in the 1500s, remember, the Catholic Church was very strong. In fact, the Catholic Church was probably as strong as many of the monarchs at the time, as far as their power or influence. And so Copernicus and the Catholic Church completely accepted Aristotle's view that the Earth didn't move. Okay? And they believed that divine scripture confirmed that it did not move. And so they were hesitant about anything that said that that was not the case. However, Copernicus couched this the right way. When he published it, on the inside, the very first, the prologue, if you wanted to say whatever it is, said, oh, this is an interesting mathematical idea and concept to think about. It may not have anything to do with real life. So he kind of said, oh, this is something to think about. He didn't say this is the way it was. Okay? But he didn't realize what this little book, is not very big, it's actually a very small book, would change the way people started thinking. All right? And so that takes us to our next guy. And I'm going to do our next guy in a new video, so here we go.